All right, here we go. We're going to continue to talk about electrolytic cells. We've talked about molten cells, but you recall that we can also create an electrolytic cell if we can dissolve a salt in water and have an aqueous solution. There is a complication with that though, because water can get involved in the process. Water can both oxidize and reduce. And so really before we can get into this all the way, we have to think about just water by itself and what it can do. Okay, so when you think about your reduction table, you can look through there and find these two reactions. The reduction of water, of course, that's easy to find in there because it's a reduction table. And so you'll have two water molecules. Really what's happening there is the hydrogen is reducing. You're going to produce hydrogen gas. You gain a couple of electrons. You'll make some hydrogen gas, okay? And you're also going to make some hydroxide ions along the way. Okay, that's the reduction. This has a reduction potential of negative 0.83 volts. Okay, so water doesn't want to reduce, but you can force it to reduce. Mm-hmm. Okay, now you can also find in there the oxidation of water. Of course, you're going to have to flip the half reaction over in order to see that. But again, you'll see that it involves two water molecules. A total of 4 electrons are involved. And what's happening here is the oxygen in water is being oxidized. And so you'll end up making some oxygen gas, and you'll also make some hydrogen ions. And this has an oxidation potential of negative 1.23 volts.
Wow, you got those voltages memorized, Mr. Hevel?
Well, I would hope that all of you have memorized your reduction table by now.
Oh, yeah.
Isn't that a given, Mr. Moore?
I assume so.
Yeah, I assume it is. Okay. Now, we can come up with a total reaction if we add these halves together. Of course, we'll have to double the top one, so our electrons will cancel out. So when I do that, when I double the top one, I'll have 4 water molecules plus 2 more here. I'll end up with a total of 6 water molecules on the left. Of course, the electrons will have canceled each other out. Mm-hmm. Because I'm doubling the top reaction. I'll end up with 2 molecules of hydrogen gas. Okay, we'll end up with a molecule of oxygen gas. Okay, and then I will also end up with, you know, Mr. Moore?
Yeah, there needed to be 2 OHs there.
Yep, that should be a 2. Sorry about
Yep.
that. So when we double the top one, we'll have plus 4 hydroxide ions, and we have 4 hydrogen ions here. And of course, the hydrogen and hydroxide, we could combine these together to make 4 water molecules. Mm-hmm. So you'll have 4 water molecules there, 6 over here on the left. We can cancel 4 from either side. So the big finish, we'll end up with 2 water molecules, and we'll make 2 hydrogen gas molecules. We'll make an oxygen molecule, and we'll end up with a cell potential of negative 2.06 volts. Mm-hmm. So water does not want to go through this process, but if you can supply something greater than the 2.06 volts positive, you can force the water to electrolyze. Okay?
Yep.
And so we have set up in the back here an apparatus to do this. This is called a Hoffman Apparatus, and it's specifically designed to allow you to electrolyze water and to capture the gases as they're being produced.
So there's our power supply that gets plugged in. We have to force this reaction to happen. That's what electrolysis is about. So we've got our anode and cathode down there, the red and the black.
Yep.
The electrons get pulled into the power supply at the red. So this yellow wire is attached to the red. So whichever of these is leads is attached to the what would I watch that go rolling off? This is where the electrons are getting taken from. That would be the oxidation. They go through the power supply and they come through the wire that's attached to the black terminal. Through this would be the cathode, where the reduction is happening.
Okay, so let's flip it on and see what happens.
All right.
Excuse me. All right, so we'll turn on the power supply. Now we have to turn up the voltage, because remember we need something greater than 2.06 volts. So you can see the voltage going up here, and now we're just starting to get some bubbles. And now I'm just going to crank the voltage up, and we can see that we're getting plenty of bubbles produced at our electrodes.
What is that metal? That metal that's right there.
That is platinum.
The real thing?
It's the real thing, indeed.
Mm-hmm.
For once
So we
we're
do
not-
have platinum in the department.
We do. For once, we're not using cheap graphite electrodes.
Oh, let's close the top too.
Okay, so now the idea with this is there's valves here, and I can close those valves, and then we can capture the gases. And as we collect gas volume, it'll push water up through the middle, and there's a reservoir up top, so that you can electrolyze a fair amount of water and collect a noticeable volume of each gas.
Looks like the levels of water are not the same.
That's interesting. I wonder why that would be.
Should they be?
Well, I guess if you look at the balanced equation, you'd start to realize, well, maybe they won't be the same.
No. Oh. Looks like there's 2 hydrogens made for every oxygen.
Yep,
Did we read that right?
I think you're right. So we can see, yeah, we're collecting more gas over here. This must be where the hydrogen is collecting. Okay, this is our negative post on the power supply, which is the cathode. There's reduction going on here.
Mm-hmm. The hydrogen's reducing.
Yep. And then the other side over here is our oxygen. And this is our anode. This is where oxidation is going on. And that's what's happening to the oxygens being oxidized. And notice as we collect gases, we're starting to push water up the middle here.
Yeah, the water has to have some place to go. It gets pushed down by the gases. So then, yeah, the water winds up getting pushed down into there and then going up through that middle tube, and kind of hangs out up there in that bulb.
This is usually where I forget about the apparatus and start talking and let it overflow out of the top like a fountain. We'll try to avoid that.
So it looks like we're doing pretty good. We've got
Yeah.
a fair amount of gas collected.
Do we have enough that we can test them, you think?
Oh, how do you test?
Well, the test for hydrogen is to collect it in a test tube and put a lighted wood splint under it, and it should explode.
That sounds like something we'd like to
We
do.
would like to do. Okay, do we have enough there, Mr. Moore? Can we do it?
I think so.
Okay, so I'm going to shut this off. Okay. And I'm going to try to gradually let the hydrogen flow into the test tube, and then we'll try the wooden splint and see how that works. I usually try
Yeah,
to
I
just...
guess the hands are in the way, but yeah, he's releasing the valve, allowing the hydrogen to get pushed up into that tube. You see the hydrogen? Oh, well, the water is going back up.
Okay.
Okay, do you want me to light that?
Well, if you would, Mr. Moore, that'd be great. Okay, so now in theory, I put my thumb under it. I shouldn't have had to do that because the hydrogen's less dense than air.
Mm-hmm.
Let's see what happens. Oh, wasn't that a nice little pop? That's the positive test for hydrogen. Now let's try the oxygen. Same thing, we're going to try to release it into the test tube. Uh-oh, come on. I don't know how much oxygen we got in there, Mr. Moore. We got some. Okay, so now here's the test. We put a glowing splint in, and hopefully it reignites.
Oh, it did.
Did it?
Yeah, there it is.
There it is. I don't know how easy you could see that.
Yeah, we didn't get quite enough oxygen to fill the tube,
Yeah,
did
that
we?
was the problem. For some reason, it wouldn't go all the way up.
Oh. Okay. So anyway, yeah, we did confirm that there was both hydrogen in the one and oxygen in the other, demonstrating that water can be split up into hydrogen and oxygen with that external source of power.
Another successful demonstration.